So in the last class, we stopped at calculating the moments and the torsional stiffness for open and a closed section, and then the comparison was that the closed sections are almost 300 times more stiff in torsion as compared to open section. So we will just do a short exercise in which we are comparing the shear stress in the cross section in both open and closed. So for the closed section, we know that 2AF is equal to H11 kappa 1. This is for the closed section. So the torsional stiffness would also be for the closed section. And then the maximum shear stress would be written as M1 over 2AT, where if you recall, area is of the section which is enclosed by the closed section thin wall beam, right? And in case of an open section, this superscript is just for open, so it will be equal to 2G kappa 1 T over 2, and it's so it's the area which is enclosed by the section. For example, this.
The professor did it last time as like a cursive A, like he put like a squiggle on the end of it.
Okay.
Yeah.
Like this.
Yeah. Like
okay.
That.
Yeah. And so essentially you would get that this is 3m1 over LT square on simplification, and then you can just take the ratio. So and then you can cancel off terms. So essentially you'll get 3R over T. R is this distance and T is the thickness. Right. So for the same ratio which we took for the comparison of stiffnesses, that the thickness is almost 10 times less as compared to the radius. So tau max for the open section is closer to 60 times tau max for a closed section. So it means the shear stresses which are coming in open section are almost 60 times more than the shear stresses in a closed section. So this completes the torsion part for closed sections, for thin walled sections, and torsion for open sections was done much earlier. Now let's look at
What is the L again?
L is the length of the curve.
Okay, so like the circumference.
Yeah.
So, where did you get the 2 pi at the bottom?
So
At the top, you change the area of it.
yeah, so
pi r
H
squared.
you have to substitute the values for
if you cancel out the M1s, where do you?
Let me see.
Yeah. You cancel the M1s.
So
T, but at the bottom, where's the pi r?
LT square. So you have the value of L, and the L would be the circumference of that, so it will be 2 pi r.
So take L out of
Yeah,
it.
I have to take L out of it. Yeah, exactly. Okay, so let's look at the bending and sharing of the thin wall beams, and what are the stress flows which we can find out in when the shear force is applied on a beam which is made of a thin wall section. So just for a recap, I'll write that the axial shear flow is defined as n of x comma s, where x is the length coordinate and s is the coordinate in the cross section along the curve, and it will be sigma 1 x comma s t s, where t s is the thickness as the s coordinate varies. And then we have shear flow, which is
I'm sorry. Sorry for bothering again for on the previous formulas, but is there random 2 that was not canceling and we cancel it? Because I mean, what you brought it makes 30, not 60. So since we had 2 before in the maximum shear stress over there. Because 3 times 10 is 30.
right. Let me see. Okay, so yeah, the area has 2, moment has 2 pi r t square. Yeah, so I would make it 30. Yeah.
Okay, so the formulas are correct. Mainly
I think so.
like correct
So
formulas.
area is pi r squared t. 2 comes from here, 3. M1 cancels off, L is pi r, 2 pi r, because circumference of a circle is 2 pi r, and then t squared, so everything cancels off. So yeah, it's 30. Yeah. For the same ratio, maybe the ratio is not mentioned in Professor Rosini's notes, so maybe he took 1 over 20 and then he calculated 60. So yeah, but if it's this ratio which was taken in the previous analysis, then yeah, it will be 30 times. But as this ratio changes, that could affect the shear stress results.
Yeah, no, my concern was only formulas over there was carrying like what.
Yeah, I agree. Yeah, so this is perfect. Yeah. Okay. So the shear flow. Was defined as f of x comma s, which takes the shear stress along the curve, x comma s, t s. Okay. And we also have the equilibrium equation. Such that differential of the shear flow with respect to s coordinate plus a differential of the axial stress flow with respect to axial coordinate is equal to 0. This was derived in Monday's lecture or Friday's lecture. So, if we have to evaluate shear flow, then we need to evaluate the axial stress flow, and if there is a given loading, for example shear forces in the beam, then we can calculate the axial stress from the formulas we did in bending of a 3D beam. So if you recall, sigma 1 x comma s is essentially E times n1 x1 over capital S. So these two s are different, plus m2 x1 over h22 x3 minus m3 x1 over h33 x2. So for a beam in bending, the axial stresses induced by shear forces can be evaluated by this expression, but it makes some assumptions that the frame of reference is attached to the centroid and is a principal axis a bending frame, right? That's why we don't have any H23 term, right? Because we may or may not find symmetry in the cross section when it comes to thin wall beam sections. So now if we have the axial stresses, then we can calculate the axial stress flows by multiplying it with thickness.
Do we have to decompose like x3 and x2 into s?
That would be done later on, yeah. So x3 and x2 are cross-sectional coordinates, and as we go along the curve to calculate shear flow, they will change.
Yeah.
So we have to put those coordinate values, and it's simpler sometimes in terms of just convert x2 and x3 in terms of s. So yeah, we will have to transform them into s.
So it'll be like a mapping.
Yeah,
Okay.
exactly. So we have the actual stress flow as n x comma s E T s n1 x1 over s plus x3 m2 x1 over h22 minus x2 m3 x1 over h33. Now from the equilibrium equation we can write that the differential of shear flow with respect to the s coordinate is equal to negative of differential of the axial stress flow with respect to x1. So the differential of shear flow with respect to the x coordinate becomes minus E T s n1 x1 over s plus x3 m2 over h22 okay, so we have to differentiate this expression with respect to x1. So I have n1 which depends on x1, so it becomes 1 over s dn1 x1 over dx1. x3 doesn't depend on x1, it just depends on s, so x3 remains the same, h22 doesn't change, and dm2 x1 with respect to x1. And I'm differentiating the third term, so it becomes minus x2 dm3 x1 over dx1, and then I have h33. Okay, so for the sake of simplicity, we will assume that we do not have any actual loads in the problem. So we are dealing with just the shear forces. Um, so we assume that there are no actually distributed loads in the problem, means okay. And also if you recall, dm2 over dx1 is equal to v3 x1, and dm3 over dx1 is equal to minus v2 x1. This is from the equilibrium. For a beam in bending. I would encourage you to go at home and derive this, figure out why the signs are different. It's basically convention. The moments are defined in a particular way. It's sigma 1 dA for a particular dimension, sigma 1 x2 dA, and then for other dimensions minus sigma 1 x3 dA. So you should try this out, derive it, and see why there is a difference in the negative sign. It's just equilibrium equations. Okay, so if we make these simplifications and obtain our expression for the shear flow again, so this becomes minus ETS x3 over h22 v3 plus x2 v2 over h33. So the shear flow is associated with the axial stresses due to bending. Okay, so the bending loads generate some shear stresses in the cross section, and this is how we can evaluate them. And to further evaluate the shear stress, so this expression is still a differential of ds, so we have to integrate it over the domain. Now for example, if the curve is like this and my s coordinate starts from here, then I would have to integrate this expression for the entire domain of S, where x2 and x3 are now functions of S. They are not Cartesian coordinates, because they so let's assume that this is centroidal reference frame, which is at principal axis of bending. So I2 and I3 are aligned with the principal axis of bending, and then as you can see, when S moves along the curve, x2 and x3 change, so they do not remain constants, or they do not have a particular value of a line. But it may be simpler to calculate x2 and x3 if you have a simple cross section, like a C section for example. Then your x2 and x3 vary with S, but it's fairly easy to calculate. So now we obtain the shear flow by integrating this equation from 0 to S E Ts x3 v3 h22 plus x2 v2 over h33, and there's a negative sign there, plus the integration constant c. Right. So x3 depends on S. There is a ds. Okay. x3 and x2 depend on S. T depend on S, but v3 h22 they do not depend on S, right? So they can be outside the integral. So it becomes E3 of S x3 ds v3 over h22, because v3 depends on x1, not on S. And you have another term 0 to S ETS x2 ds v2 x1 over h33 plus c. So this entire integral is split into two parts, and then this integral is referred to as Q2, not the entire integral though. So this term is referred to as Q2 of S, because that entire term is dependent on S, but this is constant, won't change with S. And then this integral is defined as Q3 of S. And C is the integration constant. Right. So if we have a problem, we can evaluate the bending stiffnesses H22 and H33 by first forcing the frame to be a centroidal frame and then a principal axis bending frame. And then we can also calculate V2x1 and V3x1 based on the loads on the given problem. So if we want to evaluate the shear flows, we need to evaluate the integrals Q2s and Q3s. So if we have these integrals, we can solve the problem, get the shear stresses or the shear flows in a thin walled beam problem. right? So now we don't know how to evaluate that constant, right? The integration constant will be there, so we can it can be a function of x1 or it can be just a constant. Yeah, the integration is with respect to s, so c can be a function of x1 or just can be a constant.
Alright, so the other two integrals, they don't produce a constant because we have definite things. So basically, where does c come from?
So
Because we haven't solved the integral yet. So is it just because it's a partial?
So yeah, it's a partial differential equation. Even if you have the integration constants or integration domain from 0 to s, you can get c as some non-zero quantity, which you have to evaluate. But we have some other relations or other properties which I'm going to discuss now, which you can use to find out c.
Alright, so it could be a function of x1.
It could be a function of x1, yes.
Okay.
I think it should be a function of x1 in general, but because you already know where you are evaluating the shear stresses, so we can find it out. Yeah.
I guess as another question, what is Q in this case?
Q is just a mathematical quantity. We are clubbing some terms so that we don't get confused.
And that is different from the applied moment on the beam.
Yes, it's not an applied moment. Yeah, it's not that. It's Q2, a function of s, which is just this integral.
Okay.
Yeah. Okay. So when we have an open section, right, so if we look at a beam would have this shape. So if we look at this edge particularly, so the stresses at this location or on this edge are 0 because it's a free edge, right? So the stresses at this point in this beam should also be 0 in the section. So this is the cross sectional area, and this is along the length of the beam. So due to reciprocity, the stresses should be 0 here because it's free stress. So in the section at the edge, the stresses should be 0. So if I start my s coordinate from here, right, so it is evident that f x comma 0 should be 0, right? If my s coordinate starts from the edge, then the stresses, the shear stress should be 0 due to reciprocity of the free edge. So if I substitute my value back here when my s is 0, this expression should go to 0. So we have a condition there to evaluate the integration constant. Okay. Okay, so I'll quickly outline the process. So first, select your origin such that the frame is centroidal, principal. Then calculate H22 and H33 for this section. And then obtain the integrals Q2 of S and Q3 of S. Okay, so let's do an example. We have a cross section I'm marking star for the centroidal principal axis bending frames. Now the dimensions are such that this height is h. So the centroid will be at h over 2 because it's symmetric. And this width is b. Okay. So in any thin wall beam problem, if I have multiple segments such as this in C section, I have the freedom to choose my S coordinates direction. So I can choose S1 in this direction. I can choose S2 for the segment 2 in this direction, and then for the third direction I can choose my S3 starting from this open section, open end. And the reason for choosing this is that the calculations become simpler. I can just use the same condition fx comma 0 is 0 and evaluate the integration constant easily at that location. So so I2 star, I3 star is a principal centroidal frame of reference. Okay. And let's say that V2 is 0. So we have a non-zero V3. So we are applying shear force. Yeah. I2 coordinate of the centroid is, let's say this distance is d. So is b over 2 plus h over b. Okay. So now I have to evaluate the shear flows. So the shear flow is written as C minus Q2 of S V3 over H22, right? So for this section, if we have to calculate H22, that becomes E times 2 1 over 12 BT cube plus BT H over 2 square plus 1 over 12 TH cube. So this T cube is going to be very small. So this entire term goes to 0. So if we simplify this expression, we obtain h cube over 12 from this term plus b h square over 2 times t. So we use parallel axis theorem for the two sections, the top and bottom segments, and then simple expression for this rectangular section. Now let's look at the segment 1. F of S1 is going to be C minus Q2 of S1 H22 times V3. So Q2 of S1 is going to be integration 0 to S E times T x3 ds. So what should be x3 in this case? So this is our centroidal principal frame. x3, when S1 moves from 0 to S, x3 remains h by 2, right? When S1 goes from 0 to its domain S, the coordinate x3 remains h by 2, right? So I'll just substitute 0 to S E times T h by 2 ds. So upon integration, we'll get Et h over 2 S1. So it's very important that we evaluate the values of x2 and x3 correctly for the calculation of integration constants. So in this problem we do not have v2, so we only need values of x3. We have only non-zero v3, and then as s coordinate moves from its domain 0 to S1, we can calculate what's x3, and that's h by 2 for the top, the first segment. And if we impose the boundary condition, f of S1 goes to 0 is 0, so it implies that C is also 0. So let's say this is C1, so C1 is 0. So yep,
V2 to V0 medium.
this is the problem.
Okay. we'll
Like,
just give it.
yeah, just
Okay.
it's given. It's for simplification. We are trying to see what values x3 takes
Okay.
along S. So we took v2 0. So now the second segment, which is easier to calculate, is this one. So let's find out f of S3 when I know that f of S3 is equal to 0 is also 0, because it's an open end here. So f of S3 can also be written as C3 minus Q2 S3 over H22 V3, right? So this gives C3 is 0, and now I have to evaluate Q2 of S3, which is equal to integration 0 to S3 E T x3 ds. So what will be x3 here when S3 goes from 0 to S3 or the entire domain 0 to B. Yeah. So it will be 0 to S3 E times T negative H over 2 ds. C3 is 0, yeah. Because we have an open edge here, so because of reciprocity, this entire term goes to 0 at 0. So this will be 0, but this won't. So C3 goes to 0. Okay. So we have this becomes minus ET H over 2 S3. Right. And let me keep it. Okay. Yeah. Just take this off. Okay. Now for the segment which is the second segment. So we are looking at this vertical section of the thin wall beam section. So okay, so we don't have any free edge, neither we have a free edge here nor we have a free edge here, right? So but again we have the same condition. For example, if we zoom this out and try to draw it here, we have an edge like this, right? So if we calculate the shear flow or the shear stress in this segment at this location, for example, this is my 1 and this is my 2, I have the shear stress here in this segment evaluated using the expression which we calculated here for the first segment. Then I can say that my shear stress in the segment 2 at that location when S2 is 0 should be the same, right? Because of reciprocity. We are using this condition at the free ends to equate it to 0, but now it's not a free end, it's not a free edge, so we can use the reciprocity again, evaluate the value at this point on this segment using the shear flow equation we developed there and equate it to that. So that will be our boundary condition in this case. Yeah. It should be the same, but let's look at it. So the magnitude is same for sure, and true.
Yeah, like if S1 is negative or it's positive.
So at top it should be the same, at the bottom it should be the opposite.
Yeah.
Okay. What did you say?
But let me think one more time. I'm slow. Yes, exactly. So the values will change based on the S coordinate, and generally the shear flow keeps going because the shear stress has nowhere to flow. So it will be, yeah, it will be same. And
Always?
Mhm.
It's always the same?
if you are considering the direction of this S2 such that it goes away from that edge, then it will be the same.
Okay.
Yeah. But if it's converging into that section, then your conditions will change.
Okay.
Okay, so what we can write is f of S2 is equal to 0 is equal to f of S1 when it's B, right? So when we substitute f S2 is equal to 0, we get the integration constant C2. And when we substitute S1 equals to B in the expression, so we have the expression for the shear flow as minus Q2 S1 is equal to B over H22 V3. So it becomes minus ETBH over 2H22 V3. So we have a okay, so we have a negative sign here, right? Okay. So we still need to evaluate Q3 so that we can complete our calculations, or Q2, we need to evaluate Q2 of S2. So we need to evaluate Q2 of S2 so that we can complete our calculations for the shear flow. And now this becomes integration 0 to S E3x3 ds. So what should be x3 in this case?
It's a function of x.
Yes, because when S2 goes from 0 to H, x3 changes, right? It starts from H over 2 and then it reduces, right, as we go on with the coordinate S2, right? So as we move down, increase S2, x3 reduces, and because it's straight vertical down, then it becomes H by 2 minus S2, right? So we'll just substitute the value there, ET H by 2 minus S2 ds. So when we integrate, it becomes ET HS over 2 minus S2 square over 2, and the limits are for S2 right. Okay, and this becomes E times T S over 2 H minus S. So we evaluated C2 already here, and we evaluated Q2 of S2 here. So we can complete the expression for FS2 to be minus ETBH V3 over 2H22 minus Q2 of S2 over H22 V3, and the Q2 value is calculated here. Right, so we have shear flows calculated in all the three directions. So just a quick closure on the problem. This Q2 value is negative and there is a negative sign outside in the expression. So the entire shear flow becomes positive. So the direction of shear flow here will be in this direction. We have a negative expression here, and S2 comes from top to bottom. So in the segment 2 we have the shear flow in vertical direction, and then we have a negative shear flow again in the segment 1 because we had positive expression for Q2. So this is the direction for shear flow. Okay.